So generally, you can think of, we've got some true parameter value that we want to estimate. So population parameter. And we've got some estimate. Some estimator from a sample. Okay. The difference between those, what the estimate is minus the true value, that's the error, right? That's the error that the estimator made in a particular case for a particular sample. Okay. This is a random quantity because the value that the estimator takes depends on the random sample, depends on which sample you happen to get, right? So how do we tell whether an estimator is good? Well, in any particular case, we're not going to know the value of the population parameter, but we can think about some properties of the estimator. In particular, we might be interested in this difference, right? And that difference is a random variable because this is a random variable, right? If the estimator is random, and the estimator minus a constant is random. And if we want to know if that error is now a random variable, we want to know, is that error big, is that error small, right? Does it tend to be big, does it tend to be small? What would be a way of summarizing that? We could take its expected value, right? So we could take the expected value of that difference. It's a random variable. This number is always going to be positive, right? This measures how far off the estimator is. And if this thing is big, the estimator isn't very good. If this thing is small, the estimator is good, right? Because if this thing is big, the estimator tends to be far away from the thing it's trying to estimate. If this thing is small, it tends to be close. Now, it turns out to be easier to do calculus and analyze things if you work with the square instead of with the absolute value. It's arbitrary. This is one particular way of measuring how good an estimator is. And this particular thing is called the mean squared error. Mean squared error of the estimator. Okay, it's the expected value of the difference between the estimator and the thing it's trying to estimate squared. Now, remember that the expected value of x squared is generally not equal to the expected value of x squared. Right? This is not the same thing as the square of the expected value of the absolute value. It's the expected value of the square. This is in general. OK. So there are other ways of thinking about this. And here's one of them. Imagine that you have a target. And you're shooting at the bullseye. Okay. There are two kinds of inaccuracies that your rifle can have. Right? One kind of inaccuracy is when you shoot repeatedly, the bullet hits in almost the same place every time, but that place is not the bullseye. Does this make sense? OK, so this is an accurate rifle that is not sighted incorrectly. OK, you could adjust the sights so that those shots, if you did it again, those shots would all be really close to the bullseye. All right, this difference, how far off you are on average from the bullseye, that's called bias in statistical terms. OK, the spread of the shots, that uncertainty, how spread out they are from each other, that is variance or standard error. OK, so you could have a different rifle which when you shoot, thank you. Is all over the place, right? This one, it might be that if you average the location of the shots, they would average to be the bullseye, right? That somehow the centroid would be the bullseye. So this second rifle has low bias because on average you would have hit the bullseye. that it has high variance, it has high standard error, because you're typically really far away from the bullseye. It's a different kind of inaccuracy. One is sort of an intrinsic inaccuracy in the process. It's not repeatable. And the other is it's repeatable, but it's off from the mark. Okay, so in this example, you have low standard error, big bias. In this example, you've got low bias, big standard error. And they both correspond to large mean squared error. So in fact, you can write the mean squared error of an estimator is equal to the bias of the estimator squared plus the standard error of the estimator squared. All right, what is the bias of the estimator? The bias is defined to be the expected value of the estimator minus the parameter. Okay, with no absolute value sign. All right, it's just on average, what does the estimator give you? How does that compare to the parameter? So remember, expectation is linear. So this is equal to the expected value of the estimator minus the expected value of the parameter. What's the expected value of the parameter? It's just the parameter itself, right? Because the parameter is a constant. So the expected value of a constant is a constant. So this is just the parameter.